Math 2414, Parametric Curves, Video 9, some common parameterizations. For those of you heading off to Calculus 3, and hopefully it's all of you, what I'm about to show you will pay many dividends throughout the course. You'll be re-taught it or review it in that class, but I want to go ahead and show it to you now. But I'm only going to show you 3 common parameterizations, the ones that you're most likely to encounter as you go through Calculus 3. All right, the first is if you have an equation that is literally a function, y equals some function of x. There's a common, dare I say, trivial parameterization. You could say that x is equal to t and y is equal to f of t. For example, let's say you wanted to parameterize y equals x cubed minus x. Then you could just say x equals t and y equals t cubed minus t. Literally just saying, switching out x with t. This is why it's called a trivial parameterization. Really what you're doing is treating x as the parameter, but saying x equals x looks a little silly. You can also do this if you have x equals f of y. Then you can just say that y is the parameter and x is equal to f of t. So for example, if we had x equals, we'll say cosine of y plus sine of y, then you could say y equals t and x equals cosine of t plus sine of t. And you may be wondering, what is the advantage of parametrizing a function when you can just leave it as is? Well, there will be places in Calculus 3 where you do derivatives and integrals that are easier from a parametric perspective than from a rectangular perspective. I know that may seem kind of hard to comprehend at this point, but trust me. So that's common parameterization number 1. Your equation is already a function, so you let the independent variable equal t, and you let the dependent variable equal your function evaluated at t. Another common parameterization are circles. Now, not just the unit circle, but any circle. And when I say any circle, I mean a circle of the form x minus h squared plus y minus k squared is equal to r squared, which you should be familiar with because the center is at h comma k and the radius is r. Worst r in the history of r's. And the center is at h comma k. So how do you parameterize this? The way you parameterize a circle is you actually take advantage, and I'm going to show you the development of this in case you forget it. You take advantage of the Pythagorean identity cosine squared t plus sine squared t equals 1. Now this isn't the parameterization, I'm working up to it. The trick to getting the parameterization is to make the r squared match the 1. And the easiest way to do that is to multiply this whole equation on both sides by r squared. And if you do, that will give an r squared on the right and an r squared in front of both the cosine squared and sine squared on the left. And then you can just equate these and solve for x and y. If we equate the first one, we get x minus h squared equals r squared cosine squared t. If we square root both sides and just take the positive square root, we could take the negative square root, but we just need a parameterization, not all parameterizations. We would get x minus h equals r cosine t. And if we solve for x, we get h plus r cosine t. And if we do the same thing for the y's, we have y minus k squared is equal to r squared sine squared t. Square root both sides to get y minus k equals r sine t, and then add k to both sides to get y equals k plus r sine t. And so this is the parameterization of a circle whose center is h comma k and whose radius is r. Just for kicks, let's go into Desmos, take a look at that real quick. Let's see. Desmos, please. All right. So we'll say, I'm actually going to put h plus r cosine t, and we'll add sliders for those, and k plus r sine t. We'll add a slider for that. Let's get all our sliders together. But if you notice, I've already got a circle because it's defaulting a value of 1 for h, r, and k. K being the hk being the center and r being the radius. So if I increase the r, I should get a bigger circle. Wonder what happens if I go negative. Turn circle inside out. Okay. Technically, we don't have negative radii. And the h is the x coordinate of the center. So if I slide it left and right, the circle should move accordingly. It does. And the k is the y coordinate of the center. So if I slide it left and right, it should move up and down accordingly. And it does. So parametrization of a circle is easy if you know its center and its radius. And if you forget the parametric equations on the bottom, you can literally reinvent the wheel like I just did. The last one I want to show you is the parameterization for a line segment. And specifically, a line segment from one ordered pair, which we'll call x0, y0, to another ordered pair, x1, y1. So for example, let's say that you want the line segment from, we'll say that's 1 comma 3, and you want to connect it down here, and we'll call this ordered pair 4 comma negative 2. And let's say that not only do we want to connect that line segment, but we want to orient it from our first point. So this is our x0, excuse me, this is x0, y0, to our second point, which is x1, y1. You know, maybe I should say 1 and 2 instead of 0 and 1, because I keep saying first point, second point, and it would just make sense to parameterize it. Actually, I'm going to go back to 0, and I'll tell you why in a second, and 1. Because this parametrization is going to have a restricted domain for the t, and that domain is going to be from 0 to 1. So how do we do this? I'm not going to go through why. I'm just going to show it to you. All right, so your x function is 1 minus t times the first x coordinate plus t times the second x coordinate. Or rather, let's say there's two vocabulary words I haven't used yet, and I'm sorry. Initial and terminal points. The initial point is where the parametric curve initiates from, and the terminal point is where it terminates. So in this particular problem, your initial point is at 1 comma 3, but in general, we're calling it x0, y0. And your terminal point, where the graph terminates, is at 4 comma negative 2. And in this case, generically, it's x1 comma y1. So the parameterization for the x is 1 minus t times the initial x coordinate plus t times the terminal x coordinate. And the parameterization for the y is exactly the same. You just change all the x's to y's. And it may not be immediately clear why this works. I'm going to tell you so that it'll help you remember, because literally right now, at this moment, I did not have those memorized, but I remembered how it worked and I built it. Oh, by the way, t is between 0 and 1. So how did I remember it? Well, I remember that there was a 1 minus t and a t. And here's what I was thinking. When t equals 0, I need to kill off the 1 term and be left with this. And when I put 0 there, I get 1 minus 0 times x0. So t equals 0 gives me the correct x, and it gives me the correct y. When t is equal to 0, it kills off this term. This becomes 1, so we get y equals y0. So when t equals 0, we get the initial x and the initial y. So I needed 0 to kill off the 1s, and vice versa, I need 1 to kill off the 0s. And by putting 1 here and here, it kills off those. 1 times x1 is x1, 1 times y1 is y1. So putting in 1 gives us the correct terminal point. Now, I know that went by kind of fast and furious like Vin Diesel, but that's so outdated. but that's just the way that I remember how to build it. You can memorize it if you want. What would it look like for this particular ordered pair? For this particular parametric curve? Well, let's just put in all the numbers. X would be 1 minus t times the initial x coordinate, which is 1, plus t times the terminal x coordinate, which is 4. I can't bring myself to write 4t, to write t4, so I'll write 4t. And we can distribute and clean that up. Let's see, we have a 4t here and a minus 1t, so that'll give us 3t. And then the other half of this distribution will give us a plus 1. 1 second. So x is equal to 3t plus 1. And if we did the same thing for the y, it would be 1 minus t times the initial y coordinate, which is 3, plus t times the terminal y coordinate, which is negative 2. So plus negative 2t. And if we clean that up, here's a negative 2t, there's a negative 3t, so we have negative 5t. And the rest of the distribution would give us a plus 3. So I claim that these are the parametric equations for this line segment. And by the way, all the ranting I did a minute ago about having the correct initial and terminal points, I also forgot to mention that it needs to be a line, and all these equations are linear, hence we get a line. And we could check that these are the correct equations really easily by simply putting in t equals 0 and t equals 1. Remember, this is our restriction on the t's. If we put in t equals 0, all the t terms will disappear and we'll get 1, 3, which is where we started. If we put in t equals 1, we're basically adding the numbers of the equation. 3 plus 1 is 4, negative 5 plus 3 is negative 2. And that's the common way to parameterize a line segment. There are other parameterizations, but these are by far the most common ones.